We enter the realm of systems here. Now, particularly, we're going to focus on linear systems. And in this first section, we're going to aim to solve linear systems and specifically do so by graphing. So we're going to first of all develop the concept of what a system is, and then we'll get into that solving by graphing in just a little bit here. So in mathematics, we are very interested in systems, and what a system ultimately is it's going to be a group of conditions, or we might sometimes call them constraints, that are all considered to be working synchronously together with one another. So I'll just kind of simply say it's a group of conditions that are working together with one another. So to help you understand this, I want to come up with an example that's not necessarily mathematical in nature, but how it functions is the same as it functions when we deal with just strict mathematical contexts. So whenever we do use a system, we always want to have a left brace that groups all of the different conditions together with one another, and we do this in mathematical context as well. So the example that I want to use right here is the following. So we've got a system here, and each of the individual conditions are that of a tire, or maybe we should say tires, and then fuel and a driver. And so if these are the different conditions that we need to have to operate some sort of a vehicle per se, right? Now we need more than just these three things, right? But at least for the system to function, or for the car to function, we need all of these to be able to work, right? So if you had tires on your car and then you had a driver, but then if you didn't have any fuel to operate the vehicle, then you're not going to be able to function the vehicle, and therefore the system is not going to work. And this is a really important aspect of a system, because in order for a system to function, you need all of the conditions to be satisfied. So another definition is that if there is a solution of a system, then what a solution must do or must have is it must satisfy all of the conditions or all of the constraints of the system in order to be a solution. So based on this right here, we're not solving the system because we're not satisfying all of the conditions. So if we did find a situation where you had a driver, you had tires, and you also had fuel, then we would be satisfying the system, and therefore you could drive your vehicle, right? All right, so we move right away into the mathematical systems. So what you're going to see right here is you're going to see a system. We can definitely say this is a system, and the reason why we can recognize this as a system is because you've got a left brace that's grouping together different conditions. And you can see that there's going to be two different conditions. Now actually, these two conditions are both equations. So I could specifically say that this is a system of equations because every single condition is an equation in this particular example. Now, even more so, you're going to see that this first equation condition is actually going to graph a line, right? Because of the form y equals mx plus b. And similarly, this fella right here, it's in standard form of a linear equation because you've got x and y on the same side, that sort of thing. It's also going to graph a line. So we could be even more particular and say that these are not just only equations, but they are also equations that are linear equations. And so we do have a system of linear equations. What we're asked to do here is we're asked to solve the linear system, specifically by graphing. We're going to see that there's other ways outside of graphing that we can solve linear systems, but for right now we'll solve it by graphing. And so what we want to try to find really is we want to try to find the x and y value or values that are going to satisfy both the green and the purple conditions. So I'm going to start with the green condition right there. It's actually in mx plus b form. And so on the graph right here with a y-intercept of 4 and then a slope of positive 3, this is going to give me the graph of that green condition. So any ordered pair, any xy pair on this green line definitely satisfies the green condition. Now for the purple condition, I'm going to have to rewrite that into mx plus b form to graph this. So to isolate the y, I'm going to go ahead and subtract x on both sides, and that's going to yield me this equation right here that I will then just go ahead and graph. And so that is going to start at a y-intercept of -8, and then it does have a -1 slope, so it's going to go like this. So any point on this purple line is, of course, going to satisfy the second condition. So the thing is that if we want to satisfy this system, we need to find xy pairs that satisfy both the green and the purple, which means we would need to find a point or points that are on both the green line and the purple line at the same time. And of course, these two lines intersect in only one point. It's going to intersect in that particular ordered pair right there, which has coordinates -3 and -5. So it seems then that the only solution to this system is going to be the ordered pair -3, -5, therefore. Now, it's really good to be able to verify and check to make sure that that is actually accurate. So you can check to make sure that this is going to hold by plugging in your solution into the conditions and making sure that it satisfies all of them. So our first condition, the green one, so that if we take 3 times x plus 4, that's going to equal your y value. So if I do plug in the x value there, and then I plug in the y value there, and we simplify, we do get -9 plus 4 on the left and -5 on the right. And then -9 plus 4 does equal -5. So therefore, that first condition is definitely satisfied. And then you can also take the time to check the other condition. So the other condition said that if we take x plus y, we're supposed to get -8. So if I do plug in the x there and I plug in the y right there, we get -8 equals -8, and so it's satisfied there. So we can see how, since all of the conditions are satisfied, that indeed -3, -5 is a solution to the system, and it ends up being exactly the only solution to this particular system. Alright, as we move to the next one, it's basically similar in that you've got a system with exactly 2 conditions, and they're both equations, and they actually end up both being lines, so it's hence another linear system. I'm going to go ahead and take the first one right here, and I'm going to rewrite it in terms of y alone first. So what I'm going to do is I'm going to actually let's change the color here. There we go. I'm going to add y to both sides. That's going to then give us -3x equals 5 plus y. And then from that, I'm going to go ahead and subtract the 5. And then that will then finally give us that -3x minus 5 is equal to y. So that right there will be our first condition. I'll highlight that in green. And then similarly, I'm going to take the other equation and I'm going to solve that one for y. So how about with that one, we go ahead and subtract 6x from both sides. Then that is going to give you 2y equals -6x minus 8. And then from that, let's go ahead and then divide both sides by 2. And that will give us a final result there of y equals -3x minus 4. And I'll just highlight that in purple. Alright, so now that we've got both of them solved for y, then we can easily graph these. So the one that I have in green right there has a y-intercept at -5, and then a slope of -3. So the graph of that line will look like this. And then the one in purple has a y-intercept at -4, and then a slope of -3. So it's going to look just like that. And so any point or points where these lines intersect should be solutions to the system, since they should satisfy both. But as you'll notice right here, these lines have different y-intercepts, but they have the same exact slope of -3. So they're actually never going to cross each other. So in order to find an x and a y that's going to satisfy both that condition and that condition at the same time, it's absolutely impossible to find. So therefore, to solve this system, it's impossible. So there actually turns out to be no solution to this particular system. So there are no x and y values that will satisfy all the conditions in this particular case. In the next example right here, I just wanted to throw in some examples that will remind you of some things about lines. So with like the first one right here, if we were to graph this, we'd want to isolate y. So I will first go ahead and add x to undo the subtracting of x there, and that's going to give us then 1/5 times y equals x plus 0, which of course is just x. And then I'll take that and I will multiply both sides by 5 then, and that will then give us a final result where y is solved for alone, where we've got y is equal to 5x. So that gives you the first one right there. And then for the other equation, note that you could actually graph this if you wanted to without solving for y, and the reason why that is because this is in point slope form. So you should be able to recognize that right here, this is going to be the slope of the line of 1/3. And then this right here, because it's plus 2, is going to indicate you've got a negative 2x coordinate. And then right here, because you're subtracting 4, you've got a positive 4y coordinate. So that means that that right there is going to be a point on the line. So, yeah, so let's do this in purple again. So this means that you could graph this purple line if you plot the point -2, 4, because that's going to be a point on the line, and then just use the positive slope of 1/3 to be able to find other points that you know are on the line, and that'll give you a nice good sketch of that purple line right there. So you don't necessarily have to solve for y when it's in point slope form. The other equation that we had was y equals 5x. So that means you're going to start at 0. It's going to have a y-intercept of 0 because it's like 5x plus 0. And then it has a positive 5 slope. So it's going to go like that. And then very clearly they intersect exactly 1 point. So then you would know that their intersection point, which in this case is the point 1, 5, should be the solution to this particular system. So as I showed with the first example, you could plug 1 in for x and then 5 in for y into both of these equations. So this equation, just to check to make sure. I'm not going to take the time to do so, but if you would like to do so, go ahead. You will find that it does work out great there. All right, one last example of solving a linear system here. So as I take a look at the first condition, this green condition right here, if we were to graph this, we're going to have to solve for y, which one way we could do so is we could subtract 1/2 x, and then we'll have to multiply both sides by -3/2, which you can totally do so. One nice thing that we could do is you could take this, let me pick a different color though, and you could actually multiply by something to make the coefficients of x and y not be fractions anymore. And so, like, if you multiplied by, like, 2, let's say, like, that's clearly going to do 2 times 1/2 will give you 1. But then multiplying by 2 right there isn't really going to do much because you've got a 3 in the denominator. So you're going to have to multiply by something that is a common multiple of both 2 and 3. So actually multiplying by this number, 6, to both sides of this equation would yield an equivalent equation, but it's going to kind of clear out the denominators of the fractions and just give you whole numbers. So if you were to do 6 times half, 6 times half is going to be 6 over 2, which is 3, so you get 3x. And then if you were to do 6 times -2/3, you're going to get -12 over 3, which is really -4y. And then 2 times 6 is 12. So you've got an equivalent equation right there, and then it makes it a little easier to solve from right there, because then if you subtract 3x from both sides, you end up getting that. And then if you divide everything by -4, you're going to get positive 3/4 x, because you did a negative divide by negative. And then if you divide it by the 12 by the -4, you're going to get -3. And so that right there gives you the first condition. Now solve for y. And then for the other second equation, if we subtract the 4, you end up getting this right here. And then you're going to have to take and multiply by 3/4 to both sides to then get the y alone, which then means you'll end up with y equals, and then that'll be a 3/4 x. And then if you do 3/4 and you times it with -4, you end up getting -12 over 4, but -12 divided by 4 is -3. And so that right there is going to give you that second condition there in the purple. So we'll go ahead and graph the green line first. It starts at -3 for a y-intercept, and then it has a slope of 3/4, so a rise of 3 and a run of 4, as you're seeing there. And then for the purple condition, it has a y-intercept also of -3, and then it also has the same slope of rise of 3 and run of 4. And so that's where we actually kind of have the same lines here, right? They're exactly the same equations. So in order to find xy points that satisfy both the green and the purple, clearly like this point will, because it's a point on both lines, but also this point will, and this point will, and this point, and this point, and this point, and this point, and all of those points, right? So there are going to be an infinite number of solutions, okay? But be careful about that, because when I say there are going to be an infinite number of solutions, I'm specifying how many answers there are, but not actually what the answers are. Right? The answers or the solutions are going to be the ordered pairs that actually satisfy. So the solutions really are going to be all of the ordered pairs on the line, I guess, y equals 3/4 x minus 3. Those are going to be the solutions to the system since you have the same line. So those are the solutions, and then I'll just kind of make note that yes, there are infinitely many solutions, but again, what I'm writing just right there is just specifying the number of solutions, not actually giving what the solutions are themselves.